Welcome to Monte Carlo Integration Part
Welcome
1,
to Stochastic
Basic
Simulation
Ideas
Lesson 3,
and
Monte Carlo
Estimating the
Integration.
Error.
I am Ronald Johns. We will discuss the basic ideas of Monte Carlo's integration. We will see how to estimate the error when we approximate an integral by this method, and we'll discuss some aspects of importance sampling. In this video, we will find that using the Monte Carlo integration with 1,000 sample points, that the Monte Carlo integration point estimate of the integral of x cubed, x going from 0.5 to 1.25, is about 0.5936. This is an estimate, basically a statistical estimate. We also, using some Monte Carlo integration techniques and statistics, we will compute a 95% confidence level interval estimate of this integral. And it turns out that the endpoints of this interval are 0.56785 and 0.61937. The actual value of this integral, using just some calculus 1 techniques, rounded off, is 0.59473. Our example is this particular integral of x cubed, and we're using an integral x cubed, integral of x cubed, that is easy to compute exactly using the fundamental theorem of calculus. Why do we do this when we're talking about Monte Carlo integration? We would like to compare our Monte Carlo results with the actual value of this integral. In order to understand the Monte Carlo method for integration, we need some familiarity with random variables. What are they? What functions are associated with these random variables? How do we compute things like the mean and variance and standard deviation of a random variable, and how to compute interval estimates of the mean. Let's start with a very short review of continuous random variables. If x is a continuous random variable, then x is a function from a sample space S into the real numbers, and it will have a PDF, a probability density function. The probability density function, we'll abbreviate that P of x, for x is the function having the property that probabilities can be calculated using this density function. For a continuous random variable x, the probability that x is between a and b, greater than a and less than b, equals the probability that x is greater than or equal to a and less than or equal to b, and both of these is equal to the integral from a to b of p of x dx. For any continuous random variable x, and for any real number c, the probability that x equals precisely that number c is 0. We assigned probabilities of 0 to just isolated points. An example of this sort of thing would be, suppose you throw a dart at a dartboard and you let x be the distance of the dart in inches from the center of the board. Well, the probability that x equals 2, that the dart lands precisely at a distance of 2 inches, not 2.01, not 2.0001 or something like that, just precisely at 2, the distance being exactly 2, that probability for the distance of the dart from the center of the board, 2 inches, would be 0. The mean or expected value or average value of x is defined by the expected value of x is the integral from a to b of x times the density function p of x dx. Let's remember that all of the weight of the function p of x, everywhere where it's non-zero, is in the interval from a to b. If g is a real valued function, then g of x is a random variable, and the expected value of the random variable g of x is the integral from a to b of g of x times p of x dx. So let's look at the law of large numbers. Let's let y be a random variable with finite expected value mu sub y. Let's let y sub 1, y sub 2, y sub 3, and so on be a sequence of independent, identically distributed random variables having the same distribution as y. For each positive integer n, let's define the sample mean of n of those y sub k random variables. Y sub n bar, the sample mean, is 1 over n times the sum k equals 1 to n of y sub k's. So we have lots of sample means, one for each value of capital N. Then the limit as capital N goes to infinity of the sample mean y bar sub n is the mean mu sub y of the random variable y, which we also could write as the expected value of y. So what's going to happen in Monte Carlo integration is we will write the mean of y, the expected value of y, in terms of an integral for a particularly well-chosen random variable y. Also, we can find the mean value of y in terms of an integral. So by equating a sum and an integral, approximately equal in this case, we will get the formula for Monte Carlo integration. That means that for any positive number epsilon, a fixed number epsilon, the probability that the sample mean y sub n bar minus the mean of y, mu sub y, in absolute value is less than epsilon. The probability that that absolute value is less than epsilon goes to 1 as n goes to infinity. So what that means is that as n goes to infinity, the probability, the value of y sub n bar gets closer and closer to mu sub y. All of the probability weight of that random variable gets clustered, gets concentrated right around a small region around the point, the number mu sub y. So here's an outline of the Monte Carlo integration method. To approximate this integral from a to b f of x dx, first we're going to find a random variable x that takes values only between a and b. And let's suppose that its probability density function is p of x. We'll take a random sample, little x sub 1, x sub 2, x sub 3 through x sub capital N from a population having that PDF p of x. So the distribution of these numbers here comes from this probability distribution given by this density. Then it turns out that if we take the average of these things, 1 over n, sum k goes from 1 to n, of f of x sub k divided by p of x sub k, that will be a point estimate of this integral. So to estimate this integral, we will calculate this sum multiplied by 1 over n. So let's see why this formula, this method is going to work. Let's let x sub 1 through x sub n be independent identical random variables also having the same PDF, p of x. So they're independent, identically distributed random variables. Let's consider this sum. K goes from 1 to capital N of f of x sub k over p of x sub k. Show that its expected value is the integral from a to b f of x dx. So let's define g of x to be f of x over p of x being a real number here, lowercase x. Then we'll define a random variable, g of capital X is a random variable here, to be, according to this formula here, f of capital X over p of capital X. So let's look at the expected value of g of x. By our expected value formula that we had before, the integral, that's going to be the integral from a to b of g of x times p of x dx. But g of x, remember, is f of x over p of x. So we plug that in, and we notice that we have p of x divided by p of x here. And so this integrand becomes f of x. So what we have then is the expected value of g of x is this integral of f of x. Okay, well that's nice. So then let's see what we can do with that. We have this expected value is this integral that we're after. And now let's see what's happening here. We're going to put all this stuff together, I guess. The integral from a to b of f of x dx, according to right here, is the expected value of g of x. And that is the expected value of g of x is f of x over p of x, capital X's, random variables here. And this is approximately, by using our kind of sample mean formula, 1 over capital N, g of x sub k, summed k going from 1 to n. But g of x sub k is just f of x sub k over p of x sub k. Okay, and so we have this integral that we're after is approximately equal to this sum, where we're picking these x sub k's coming from these random variables. They all come from a population having a density function of p of x. So we have this estimation formula. This integral of f of x dx is approximately 1 over capital N sum of the, where k goes from 1 to capital N, of f of x sub k divided by p of x sub k. So if we take a random sample, x sub 1, x sub 2 through x sub n, from a population having the distribution given by this probability density function p of x, then this sum will be a point estimate of this integral. What we have up here looks like an average of n values, so it looks like a sample mean of something. The larger the sample size, capital N, is, the more probable this estimation will be close to that integral. So if you want a pretty good estimation of this integral, use a fairly large value of n here. So we could ask a couple questions. If we have this formula, we take this sample, we compute this, and say that's our estimate of this integral, how close are we? With what probability? Because remember, there's a lot of randomness built into this. The second thing that we could ask is, well, how large a sample size do you need in order to know this integral's value with a certain level of confidence? In other words, an interval estimate of the value of this integral. Those are things that we will have to discuss as we go along. First goal, find a point estimate of the integral from 0.5 to 1.25 of x cubed dx, and we'll use the Monte Carlo method to do it. So here's what we're going to do. To estimate the integral from a to b f of x dx, we're going to find a random variable x that takes values only between a and b. The range of that random variable will be the interval ab. And let's suppose that x has the density function p of x. And we could use, for instance, a uniform distribution on AB. That's probably the easiest. And as we saw before, we can rewrite this integral this way by multiplying and dividing by the density p of x, calling this fraction g of x. And so we would then have that this integral is the expected value of g of x. And we already saw how we can estimate this by picking a random sample. And so we'll use simulation of the random variable x to approximate this expected value of g of x and also the variance of g of x. And once we have those, we'll use those to find an interval estimate of the value of this integral. If x is a random variable having a uniform distribution from 0.5 to 1.25, then the PDF is going to be the following. If we think of this as the interval from A to B, the PDF is going to be 1 over B minus A, which in this case is 4/3, and that's if x is between 0.5 and 1.25. P of x will be 0 otherwise. So the graph of it looks like what we have over here. The density function is 0 until we get to 0.5. Then it jumps up to 4/3, is constantly 4/3 for x values until we get to x equals 1.25. And then P of x jumps back down to 0 the rest of the way. So the expected value of x cubed in that case, thinking of x cubed as f of x, that's going to be the integral over that interval, f of x times the density function p of x dx. And so that's going to be the integral of x cubed times 4/3 dx. And this is an easy integral to evaluate, say from the first few weeks in integral calculus. But our goal is to use the Monte Carlo method to approximate this integral. And then we can compare the approximation, the estimation that we get with the exact value of this integral, which can be evaluated using Calculus 1 techniques. So if we want to evaluate this integral using Monte Carlo techniques, thinking of x cubed as our f of x function, and p of x is on this interval going to be 4/3. We have f of x over p of x here, and then if we divide by p of x, we have to multiply by p of x too, so that this stuff does equal x cubed. And so we have to evaluate this, and we can think of this as the integral from 0.5 to 5/4 of g of x times p of x dx. And this is going to be the expected value of this function g of x. G of x in this case is this thing right here. Okay, so we're going to use Python to generate a set of random numbers, g of x sub k, k going from 1 to n, from a uniform distribution on the interval from 0.5 to 1.5. And so x sub k then, using our uniform 0, 1 random number generator, can be done this way. X sub k is 0.5 plus 3/4 times random of nothing here. Now, if random happens to be 0, then x sub k will be 0.5 plus 3/4 times 0, which is just 0.5. At the other extreme, if this randomly chosen number, pseudo-random number, is 1, then we'll have 0.5 plus 3/4 times 1, which is 1.25. And then we can calculate y sub k, realizing that that's just g sub k, and that's equal to f of x sub k over p of x sub k, which we saw is 3/4 x sub k cubed. So it's 3/4, and x sub k by our random number generator was going to be this. We'll call it many times, k goes from 1 to n, to generate capital N random values or random numbers for the y sub k's corresponding to these randomly chosen x sub k's. And so then to evaluate this integral of 0.5 to 1.25 x cubed dx, we'll just look at the limit as n goes to infinity of 1 over n, the sum k goes from 1 to n of y sub k. As n gets larger and larger, this sum by the large rule of large numbers will certainly have this as its limit. So we're going to calculate this average for n equals, I think it was either 1,000 or 10,000, using a Python program. So basically, by the law of large numbers, we have this integral is equal to the limit as n goes to infinity of this type of sum. And we've already seen then that we can write that integral as this, but the y sub k's are this, with the 3/4 out here, due to the uniform distribution from 0.5 to 1.25. And then what we need to do is to pick a large value of n to approximate this integral with hopefully pretty good, pretty small error. It's an instead of approximation, maybe I should say an estimation, because what we're actually doing is estimating the mean mu of a certain population, and mu happens to be the value of this integral. So in any case, we're going to evaluate this thing right here, this type of sum, and we'll do it with a Python program using capital N equals 1,000. And as we pointed out before, we can actually exactly find the value of this, find the exact value of this. An antiderivative of x cubed is x to the 4th over 4. And so by the fundamental theorem of calculus, we know that this integral is equal to this number right here. And so we can compare our approximation of this stuff, the approximation of the integral by this stuff, with this exact answer. So far we have that the integral from 0.5 to 1.25 of x cubed dx is approximately equal to the sample mean y bar, defined for sample of size n as 1 over n, the sum k goes from 1 to n of y sub k, where the y sub k's in this sum are equal to g of x sub k, which basically is f of x sub k, this integrand here, divided by p of x sub k, the density function, which was constantly 4/3 for this uniform distribution. To estimate the integral then by this, we will write a program to evaluate this sum where n is going to be 1,000. So y bar, the sample mean of 1,000 data values, the y sub k's, is going to be 1 over n, sum k goes from 1 to n, 3/4 times x sub k cubed. And this is x sub k right here, and it's cubed. What we have right here is exactly what we have right here. X sub k cubed is this stuff right here. 1 over 4/3 is the 3/4 that we see right here. And so we are going to evaluate this in a Python program using capital N equals 1,000. We will use 1,000 randomly selected points using a random number generator. So to find a 95% confidence level interval estimate of this integral up here, we'll use a little bit of elementary statistics. First, for the y sub k's, we'll have to calculate the variance of that set of data values, and the variance is 1 over n minus 1, the sum of y sub k minus y bar squared. Then, to find the standard deviation, the sample standard deviation s sub y, we just take the square root of s sub y squared. And then once we have that calculated, it'll be done in our Python program. We'll calculate a 95% confidence level interval estimate using the formula y bar plus or minus z.025 times s sub y, the standard deviation, divided by the square root of n. This is a critical value from the standard normal distribution, z.025. By using standard normal tables and your knowledge of an elementary statistics course, you can find that that critical value is 1.96. So now we have all the tools in order to find a point estimate of this integral and also a 95% confidence level interval estimate of this number, this definite integral. What that means is if we do this procedure many times of calculating n terms, the y sub k's, calculating y bar, calculating the sample variance, standard deviation using this formula, 95% of the time that we do this, this interval estimate will actually contain the value of this integral. We won't be sure that the interval that we calculate actually includes this integral, but we can be fairly confident because we're using a method that 95% of the time will trap that value, that integral value, inside this interval that is calculated. By an interval here, the left endpoint uses the minus sign, the right endpoint of the interval uses the plus sign. So let's look at our Python program and output. Over here in the program, we first import the function random from the library random. We're going to have to compute square roots later, so let's import the math library also. Then I'll set sum equal to 0, and I'll create an empty list xk list, and an empty list called yk list. We're setting up empty lists for generated x and y values we get by using our random number generator. I'm going to have a sum of terms with 1,000 terms in the sum, so capital N is the number of terms, 1,000. So for k in range of 1,000, we're going to let x sub k be 0.5 plus 3/4 times random number generator, uniform 0, 1. And then we'll let y sub k be 3/4 times x sub k cubed. This 3/4 came since we divided by p of x. To get g of x sub k was y sub k. Then we'll append x sub k to xk list. We'll append the value of y sub k to yk list. We're keeping these around. Actually, we really just need the second one, y sub k list, in order to calculate the standard sample standard deviation later. So then we'll add the value of y sub k to the sum, and after all of this is done, we'll take y bar and it'll equal sum over n. Actually, this statement should have been over here, unindented. but I guess it doesn't really make a difference because each time we come through here, we're updating sum. So by the time we go through this 1,000 times, we'll just be executing this one last time for the last value of y bar. So this statement should have been moved over a little bit here, but it didn't really make a difference, I guess, in this calculation. A happy accident. So then we'll print the value of n. We'll print the value of our integral approximation, which is stored in y bar. And then the exact value of the integral, remember, is 1.25 to the fourth power over 4 minus 0.5 to the fourth power over 4. And so we'll print out the exact value of the integral. And then down here, we get into the calculation of the interval estimate. To calculate s sub y, I'm first going to calculate the variance of the y values that we stored in a list, and then take the square root of that to get the standard deviation s sub y. So I'll set sum y squared equal to 0, and then for k in the range of n, which was 1,000 in this case, we're going to do the statement right here 1,000 times. Sum y squared equals sum y squared plus y sub k minus y bar squared. So this is going to be the sum of squares of the y sub k minus y bars. Then the variance, sample variance in this case, s squared, is 1 over n minus 1 times that sum of squares that we had here. And then the standard deviation of y, sample standard deviation, using that math library that we imported up here, we'll use the square root function, math.square root of var y, variance of y. Then the error for a 95% confidence level interval estimate is going to be 1.96 times that standard deviation of y divided by the square root of n. Then our 95% confidence level interval estimate of the integral is going to be y bar minus that computed error, and the upper limit of this interval, y bar plus that computed error. And finally, we will print out interval estimate of the integral is, and then that interval estimate that we computed up here, which is a list. So then, if we look at our output, we have n was 1,000. Our approximation to the integral using Monte Carlo integration is 0.5936 with all these other digits. The exact value of the integral, which was computed right here using the fundamental theorem of calculus, was 0.5947 and some more digits. The interval estimate, the 95% confidence estimate of the integral, Monte Carlo integration, was 0.56785 with some more digits here, over to for the upper limit of the interval 0.61937 and some more digits. We can see that 0.5947 was within this interval, and we would expect this to happen if we ran this program over and over and over again, the whole program. About 95% of the time, the interval that we have here would capture this exact value of the integral. Now you might say, well, that integral is very simple and easy to evaluate. Why did we use Monte Carlo integration? Well, as I think I pointed out earlier, what we did was start with a simple example where we could actually compute the exact value of the definite integral, then use Monte Carlo integration to approximate that same integral and see if we get good approximations, good estimations of that integral or not. Now, if we wanted to have even a smaller length interval here for our interval estimate, we could use larger sample sizes. The length of that interval is determined by this error that we have here, as it was y bar plus or minus the error. And notice in this denominator we have the square root of n. So the larger the value of n, the smaller this computed standard error will be. Since we're finding 95% confidence, I should point out that z sub alpha over 2 in this case is z 0.025, which turns out from using standard normal tables to about 1.96. So what did we find out when we tried to estimate this integral using the Monte Carlo integration method? First of all, we used Monte Carlo integration method with n equals 1,000. We looked at an average of 1,000 terms. The point estimate that we got was that the integral is approximately 0.5936. Our interval estimate with 95% confidence level was that the integral was somewhere between 0.56785 and 0.61937. On the upper and lower bounds of this interval, I rounded off to, I guessed, 5 significant digits. The actual value of the integral using Calculus 1 techniques to evaluate it was approximately, to once again 5 significant digits, 0.59473. And we can see that that exact value does lie between the left endpoint and the right endpoint of that confidence, 95% confidence level interval estimate. We would expect to get an exact value within the computed limits about 95% of the time. Once in a while, when you run that program, you will get a point estimate that is so far away from the exact value that it will not actually be in the interval estimate. That happens once in a while, I guess only about 5% of the time in this case. So we never know whether our integral is within that interval estimate, but we're fairly confident that it should be, because about 95% of the time that you run this sort of calculation, it will be. We have not finished our discussion of Monte Carlo integration. We'll find out, hopefully in a later video, that this type of integration method, estimating an integral, is very useful for multi-dimensional integrals. Multi-dimensional integrals, if you use standard techniques of numerical analysis by just subdividing intervals into lots of subintervals in higher dimensions, can end up with sums that are very large. And it would take maybe millions or billions of evaluation points to get a good estimate of an integral. Monte Carlo integration is one way to get around this problem. Secondly, we can pick this density function that we use in our calculation, p of x, in a way to give us a better estimate of the integral. In our example, we used p of x being the density function of a uniform distribution, but perhaps a different distribution to estimate the same integral would be better. And this topic is called importance sampling. Thank you for watching this video. If you liked it, please hit the like button. If you didn't like it, well, please hit the like button. Have a nice day, and goodbye.